output of metal is more than 350 million tons a year. Almost all of it goes through a forming process. Metal forming means pressing, squeezing, or rolling metal into shape, as opposed to machining it. Forming depends on a basic property of metals, plasticity, the ability to change shape under pressure. By forming, ingots are changed into usable shapes. At the same time, the internal structure of the metal is altered. The rim of the ingot on the left of the micrograph is made up of long columnar crystals, in contrast to those further towards the center. Metal with this kind of structure tends to be brittle. During forming, the structure will become finer and more uniform. The most important of all the metal forming processes is hot rolling. This is a slabbing mill. It feeds a series of mill stands extending over 1/5 of a mile, which produce wide steel strip. The slabbing mill reduces these 14-ton ingots into slabs about 8 inches thick. As the rolls bite into the steel, the crystals are all the time breaking down and forming again, making the metal tougher and more resistant to failure. The slabbing mill is operated from a control room, the pulpit perched astride the rolling line. The mill is in continuous operation day and night. The chief operator and his assistants work 8-hour shifts. The operator gauges the thickness of the slab to a fraction of an inch. He sets the bite made by the work rolls. His controls direct the rams which manipulate 7,000 tons of steel every day. Edging passes reduce the slab to its proper width. To allow the slab to pass through, the top roll is raised to nearly its full height. The 2 rolls give this mill its name, a 2-high reversing mill. When the ingot has been rolled down to a slab 8 inches thick, it is sent to the shears. The shears crop the slab into the correct lengths for the roughing mill. a group of 4 high mill stands in series. The slab is now under an inch thick and is ready for rolling into strip. The 6-stand finishing mill does this. As the strip passes each stand, it gets thinner. It leaves the mill at 2,000 feet per minute, over 20 miles per hour. The strip hurtles down the run-out table, cooled by jets of water as it goes. At the end of the table, it is wound on a coiler. While one end is coiling, 400 feet away, the other end is still being reduced. Rolling has given the strip a fine, regular grain structure. Its properties are better balanced. It is tougher now and more ductile. Such hot-rolled strip has many uses. For example, steel pipe for household gas and water is made from it. Here it is being reheated in a tunnel furnace. When it leaves the furnace, the strip is bent into a tube by forming rolls. Further rolls press the edges of the tube tightly together for butt welding. The tube is cut into lengths by a flying saw, and the sections shoot away to a cooling rack. As with steel, most non-ferrous metals are hot rolled. This is a slab of copper, just off red heat, and covered with a thin layer of scale. The slab passes between the bottom and middle rolls. And comes back between the middle and top. Because of its 3 rolls, this is called a 3-high mill. As a rule, hot working does not need lubricants because the metal scale prevents sticking. The work rolls are cooled by water. After the hot rolling, metals often undergo another rolling process. This time, cold. In cold rolling, lubricants are very important. Lubricants are used to reduce friction. They increase the reduction that can be made on each pass. They carry away some of the heat produced and improve the surface finish. In all metal forming processes, the loading on bearings and gears is very heavy. Lubrication is critical. Rolling mills are generally lubricated by oil circulating in a large system complete with coolers, filters, and storage tanks. A high proportion of steel strip is also cold rolled using a dilute oil emulsion. Here, strip from the hot mill is passing forward through 3 mill stands in succession to be reduced to a 1/30th of an inch, a common thickness for car bodies. After cold rolling, strip has an extremely good surface finish. But the regular grain structure it acquired in hot working has disappeared. The grains have been lengthened in the direction of rolling. The metal has become harder and stronger, but less ductile. Sometimes this is satisfactory, but sometimes the softness and ductility must be restored. This is done by annealing. In one process, the metal is heated inside a container filled with an inert gas to prevent oxidation. This is known as bright annealing. Here, the heating is done by gas or oil, and the whole process lasts for several hours. Annealing recrystallizes the metal and restores its regular grain structure. Cold rolling followed by bright annealing gives much the same result as hot rolling, but with a better surface finish. After annealing, the strip can be worked more easily and is less liable to crack. In this tube mill, an oil emulsion lubricates and cools the strip as it is formed up into a tube. The edges of the tube are welded between rotating copper electrodes. Rolling, a continuous process, produces material in bulk. Forging, old as the blacksmith trade, remains unsurpassed for making individual parts, especially those of intricate shape or great size. By hammer or press, an almost finished article can be made directly from red-hot ingot or billet. This 170-ton mass of steel is to be forged into a turbo generator shaft. The 7,000-ton press squeezes the metal as much as 8 inches at a stroke. A skilled forge master can work even such enormous masses as this remarkably accurately, though of course a good deal of machining will still be necessary. Drop forging, used for small parts, can reduce machining to a minimum. The billet is placed between shaped dies, one on the anvil and one above on the hammer. The impact of the upper die causes the metal to flow in such a way that its grain follows the shape of the die. This gives the workpiece great toughness. After the roughing out, the crankshaft is put between finishing dies. Sawdust helps to prevent the metal sticking. When the flash has been cut off, the crankshaft will require very little machining. Fine and regular grain structure is an important asset of forgings. The forging of railway car wheels has been greatly speeded up in recent years by linking many forming processes into a continuous sequence. After rough forging, the wheel needs a period of reheating before it is taken to be rolled out to its final diameter. The dishing press forces the hub up to give the wheel extra rigidity. Forging from a solid billet is also used to make the very best seamless tube, such as that used for oil drill pipe and high-pressure steam. In rotary forging, the two forging rolls are slightly inclined towards one another to break open the center of the ingot, which flows over the piercer held on a mandrel. A cool piercer point is used for each ingot. piercer produces a thick-walled tube of medium length. This has to be elongated and its wall thickness reduced. This is done in the plug mill. The thick-walled tube from the piercer is elongated by squeezing over a plug between the rolls. Much hot-formed tube is subsequently cold drawn, and here lubrication again becomes essential. This machine draws up to 400,000 feet of seamless tube a day. Large volumes of drawing lubricant are supplied to the dies to reduce friction and to carry away the heat generated by the deformation of the metal. As the tube is drawn between the plug and die, both the diameter and the wall thickness are reduced, and the tube correspondingly lengthened. For some small diameter tubes, the plug is not mounted on a mandrel, but is allowed to float in the tube. The tube is pointed or swaged to allow it to pass through the die. The drawing of wire is a similar cold process using dies. Copper wire often starts as coils of rod produced by hot rolling. To keep production continuous, successive coils are welded together. The die reduces the rod's diameter and at the same time lengthens it. Each die may make a reduction of, say, 30%, producing very high local pressures and temperatures. This tends to cause heavy die wear, and dies are therefore made of very hard materials, such as tungsten carbide and diamond. Even so, lubrication is of the utmost importance to keep die wear to a minimum. In modern continuous machines, capstans pull the wire through a number of dies in succession. For the finest gauges, the wire may have to be drawn through 30 or 40 dies. Dies of any required shape are also used in the extrusion process. In extrusion, metal is pushed through the die instead of being drawn. Extrusion is usually carried out hot. This copper billet is just at red heat. A ram applies a pressure of up to 1,500 tons. Such copper extrusions are widely used for making electrical gear. Extrusion produces an accurately shaped section with a good grain structure and a fine surface finish. Since the dies are readily changed, a wide variety of sections can be made in one extrusion press. Impact extrusion forms the hundreds of millions of tubes, which today contain everything from glue to toothpaste. Here, little slugs of aluminum are hit by a punch and flow over it to form a tube. Pressing and deep drawing of sheet are used to produce a great variety of shapes. Steel strip up to 73 inches wide can form a whole car roof at a single pressing. It is this ability of metal to flow which makes possible a multitude of manufacturing processes. Gear blanks are turned out in quantity by multiple forging presses. Wire is drawn down to a diameter of 1/1000th of an inch or less. Aluminum can be rolled to paper thinness with perfect accuracy. The knowledge and skill of metallurgists, mechanical engineers, production engineers, lubrication specialists, all combine to improve old methods and develop new ones. All forming processes, large and small, depend on plasticity, the fact that metal can be made to alter its shape under pressure. It is on forming that the world relies for converting nearly all the metal it produces into shapes to serve its many needs.